Imagine falling toward a place where light cannot escape. No sound, no warning, only darkness. At first, everything feels normal. Your heartbeat is steady. Your instruments still work. The stars still shine. But ahead, space begins to bend. Then time. And once you cross that invisible boundary, there is no turning back. This is the journey beyond the event horizon. Black holes do not begin as monsters. They begin as stars, massive stars, burning for millions of years in a delicate balance between gravity pulling inward and nuclear fusion pushing outward. As long as that balance survives, the star lives. It shines. It creates the elements that will one day form planets, oceans, and even life. But stars are not eternal. Deep inside their cores, fuel begins to run out. Hydrogen becomes helium. Helium becomes heavier elements, until eventually iron. And iron changes everything. Unlike lighter elements, iron cannot release energy through fusion. The outward pressure weakens. Gravity takes control. In less than a second, the core collapses inward with unimaginable force. The outer layers explode into a supernova bright enough to outshine galaxies. But deep inside that explosion, if enough mass remains, gravity continues collapsing matter until even light can no longer escape. A black hole is born. Most people imagine black holes as cosmic vacuum cleaners, pulling everything around them into darkness. But that is not what makes them extraordinary. If our sun were replaced by a black hole with exactly the same mass, Earth would continue orbiting almost exactly the same way. The real danger is not gravity alone. It is density. Imagine compressing the mass of the sun into a sphere only a few kilometers across. The gravity near that object would become so extreme that spacetime itself would begin to bend. Eventually, a boundary would form, a point where escape becomes impossible. This boundary is called the event horizon. It is invisible. It has no surface, no sound, no warning. And yet beyond that line, the escape velocity becomes greater than the speed of light. Nothing can return. Not particles, not signals, not information. Black holes do not trap you with force. They trap you with geometry. If black holes emit no light, how do we know they exist? The answer lies in what surrounds them. Gas, dust, broken planets, and even entire stars can become trapped in the gravity of a black hole. But they do not fall in immediately. Instead, they begin to orbit faster and faster. As particles collide, friction rises. Temperatures reach millions, sometimes billions, of degrees. Matter begins to glow. X-rays are released. And a brilliant structure forms around the darkness, the accretion disk. Ironically, some of the darkest objects in the universe reveal themselves through some of the brightest environments in existence. But black holes do something even stranger. They bend light itself. As starlight passes nearby, gravity curves its path, distorting entire galaxies into arcs and rings. This effect was first predicted by Albert Einstein. Near a black hole, that prediction becomes reality. For decades, black holes existed only in equations. Scientists believed they were real. Mathematics predicted they were real. But no human being had ever actually seen one. Then, in 2019, everything changed. A global scientific project known as the Event Horizon Telescope collaboration connected radio observatories across Earth, effectively creating a telescope the size of our planet. Their target was a supermassive black hole inside the galaxy Messier 87, 55 million light-years away. After years of collecting and processing enormous amounts of data, humanity finally saw something extraordinary, not the black hole itself, but its shadow. A perfect circle of darkness surrounded by glowing plasma. Exactly as Einstein's theory predicted more than 100 years earlier. For the first time in human history, black holes were no longer mathematical predictions. They had become visible. If you were falling toward a black hole, the first thing to change would not be your body. It would be time. At first, everything would feel normal. Your heartbeat would remain steady. Your instruments would still work. The stars would still shine. But according to Albert Einstein's theory of relativity, gravity changes the flow of time itself. The stronger the gravity, the slower time moves. Near Earth, this effect is tiny. Near a black hole, it becomes extreme. From your perspective, your watch would continue ticking normally. 1 second, then another. Nothing would feel different. But to someone watching from far away, your movements would begin to slow. Your gestures would appear delayed. Your signals would arrive farther apart. The closer you fall, the slower you appear, until eventually, to the outside universe, you seem almost completely frozen. As you fall deeper, light itself begins to change. Every photon trying to escape the gravity of the black hole loses energy. Its wavelength stretches. Its color shifts. White becomes orange. Orange becomes red. Red becomes infrared. This effect is known as gravitational redshift. To a distant observer, the light reflecting from your suit would slowly fade as your image becomes darker, colder, and harder to detect. Eventually, you would disappear from visible light entirely. But from your perspective, something even stranger happens. The stars around you begin to bend. Galaxies distort into arcs. Light wraps around the darkness. The universe ahead seems compressed, while the space behind you becomes warped beyond recognition. You are no longer moving through normal space. You are moving through curved geometry, shaped by gravity so extreme that even light can no longer travel in straight lines. Eventually, you reach the boundary itself, the event horizon, the point of no return. Many imagine it as a wall, a flash of light, or a violent shockwave. But in reality, it may feel like nothing at all. If the black hole is large enough, you might cross it without any physical sensation. No impact, no warning, no visible line in space. And that is what makes it so terrifying. Because the moment you cross, something fundamental changes. Outside the event horizon, you still had choices. You could turn around, accelerate, escape. But inside, every possible path through spacetime leads only one direction, deeper inward. Even light cannot find a way out. Not because something is pulling it back, but because outward itself no longer exists as a physical direction. Inside the event horizon, your future has only one destination. Now something impossible happens. Two observers witness the same event, and both are correct. From your perspective, you continue falling. Your watch keeps ticking. Your thoughts continue. You cross the event horizon and move forward as if nothing unusual happened. But to someone far away, you never seem to cross at all. They see you slowing down, fading, turning redder and dimmer, until your image appears frozen forever at the edge of darkness. This is not an illusion. It is not a trick. It is relativity. Two observers. Two timelines. Two realities. Both mathematically correct. Near a black hole, reality becomes dependent on where you stand and what you are capable of observing. And the deeper you fall, the stranger that reality becomes. As you fall deeper, gravity stops pulling equally. Your feet, being closer to the black hole, experience stronger gravity than your head. At first, the difference feels small. Then it grows. Your body begins to stretch. Molecules separate. Cells deform. Chemical bonds begin to fail. This process is called spaghettification. The name sounds harmless. The reality is not. It is not fire. Not impact. Not explosion. It is gravity itself pulling every part of you at different speeds, slowly turning matter into an impossible stream of particles. Inside the event horizon, something even stranger happens. Space and time begin to exchange roles. Outside, you can move left, right, forward, or back. Inside, those choices disappear. According to general relativity, Moving toward the center becomes as unavoidable as moving toward tomorrow. You do not choose to fall. You cannot stop. You cannot turn around. Because the singularity is no longer just a place. It becomes your future. Every atom, every memory, every second of your existence now points only one direction: deeper. At the center of a black hole, physics predicts something impossible: a singularity. A point where density becomes infinite, volume becomes zero, and spacetime curves beyond anything our equations can describe. General relativity predicts it. Quantum physics resists it. And between those two theories, science reaches a wall. We do not know what truly exists there. The singularity may be real, or it may simply mark the edge of human understanding. A place where mathematics continues, but physics stops answering. And one final question remains: what happens to information? In physics, information should never truly disappear. But black holes challenge that rule. Something falls inside, where does its information go? Is it destroyed? Hidden? Encoded on the surface? When Stephen Hawking discovered black holes could slowly evaporate, the mystery only grew deeper. Even today, the answer remains incomplete. Which means black holes may not just reshape matter, space, and time, they may redefine reality itself.